Hello, ladies and gentlemen. Today we are going to go over energy transfer. What you need is your notes. Please, please, please take notes. You need them. And get your reference table up because you will need that. All right, first things first. We have this thing called the energy budget. That is all the energy that we get from the sun that kind of does like a cycle thing. Whatever we take in, we give out. Okay? So first things first, 100% comes in. But then 30% of that gets reflected either by the surface, clouds, or atmosphere. And then once the 70% gets in, it's either absorbed by the atmosphere and clouds or by the land and the ocean. Now only 51% hits the land and the ocean. That's what we absorb. And then it gets all released back out. So when it's nice and sunny and warm, the sun hits us, we're absorbing. When the sun goes down, that's when stuff is released. And it's either released from the surface or from the atmosphere and clouds. All right, so we're going to look at temperature and heat. So this is the transfer of temperature and heat. So first things first, you have conduction. That's the flame's heat causes molecules in the pan at the bottom, right here, to vibrate faster, making it hotter. And these vibrating molecules collide with their neighbors, so they start bouncing and back and forth into each other. And this vibration starts going faster and faster and faster and faster, which causes heat to transfer. This vibration causes heat. And it does it mainly on the bottom, but then you see it starts going up on the side. This is how the flame's heat is transferred to the entire pan, because it starts in the middle, it starts vibrating, and then the vibrating hits and hits and hits and hits. It goes to the whole entire thing. Why does it work best in solids? Well, that's because solid particles are next together. They're like right next to each other. That's what makes it solid. Liquid, they're kind of flowy next to each other, and gas, they're just like as far apart as possible as they can get. Then you have this thing, convection. We've seen this before in the mantle when we were looking at plate tectonics. So it's the heat in the pan, we're still looking at the pan, causes molecules of the fluid that's inside, or gas, at the bottom of the pan to vibrate faster. Remember, these are typically farther apart, but when they start moving, they don't have to bump into each other. They can kind of flow. And as they flow, the fluid heats and it rises because it becomes less dense. And then as they rise, they start to cool and they become more dense and sink. So that's where you get this action right here, which we saw in the mantle. This creates a circular pattern called the convection current. So we have that in the mantle. Now we're going to look at that in the air. Air currents causing clouds and whatnot. And last but not least, we have this thing called radiation. The heat being generated radiates in waves into the surrounding air. This wave motion is how energy of the sun travels through the vacuum of space. So I don't know if you've ever seen any like hot pavement or a heater vent and you look and it looks like there's the waves coming off it. You're seeing some of the air particles moving around because of the radiation of the heat that it is giving off. All right, so now if I'm looking at this pan, and I want to label it all, how would I do that? Well, first off, I'm looking at the arrows over here. These arrows coming off, that's going to be my radiation. The circles, that's going to be convection. Remember, convection does those circles. And then the hot pan handle, because it is metal and the metal is heating up on the side, that's a lot of the reasons why you guys have rubber on your pots and pans to protect your hand. And that does conduction. This guy's going to have a burnt hand soon. Okay. So in science, we usually measure temperature in degrees Celsius. Sometimes you need to convert to Fahrenheit and Kelvin. Well, what the heck is temperature? Temperature is a measure of average kinetic energy, how fast these particles are moving, in a sample of matter. And notice it is the average. It's not just like one specific place. It's the average. That's why, think of it this way. If you have a thermometer, you're getting the average of the whole area. It's not in just hopefully one particular spot. If you don't remember, how to do stuff like this, like how to switch between or convert between Fahrenheit, Celsius, and Kelvin. Page 13 right here. This tells you how to do that. You can just say, I wanted to say, hey, if water boils at 100 degrees Celsius, what is that in Kelvin? All I have to do is look up here at that line and follow it across Kelvin. The same with Fahrenheit. Okay, so another thing you have is this duration and angle of insolation. That's how long are we being hit with the energy. So the duration is the first one, the angle is the second one. In the winter, the sun's path is shorter. See how short that is? It's kind of flatter to the ground. So there's more area being heated by a small little bit with a lower angle. So that means less heating. Whereas in the summer, we're getting more direct. It's hitting us not dead on, but like a lot more. And you see that it's a longer line or a longer path, but it's higher in insulation. That means a smaller area is getting heated a lot faster. It's a lot smaller, so it gets heated faster. Yeah. All right. So there's some factors into this heating thing. What factors? Well, you've got land versus water. Different substances heat and cool at different rates. Now, how would I know this? How could I get this if I say I never told you this? Well, if you look at your reference table over here in the specific heat, it tells you how much energy is needed to heat something up. So look at liquid water, 4.18 joules per gram degrees Celsius. That's it takes 4.18 joules per gram of water to heat at 1 degree Celsius. That's a lot. Whereas if you look at, say, basalt or even granite, that's what the continent, remember the continental plate is typically made from, is granite, and that's 0.179 or 0.79. That's going to heat a lot faster than water because it takes less energy. So land heats and cools faster than water. Well, what about light and dark? Have you ever worn a black shirt as opposed to a white shirt outside? You typically get hotter in the dark shirt than you do in the light shirt. Different colors heat and cool at different rates. Dark heats faster than light. Okay, so then you have texture. It will affect the rate of heating. So think of this. I'm going to take some color in with this. Say I have a field covered in snow, and it is flat. And then I have a forest covered in snow, but with evergreen trees, you know, the green ones. So I have that. Which one is going to heat fastest? Well, the trees are going to heat faster. The rough land is going to heat faster because look at this. The sun hits and it starts bouncing off all that stuff. All that energy hits and starts bouncing off. And it's kind of like insulated, kind of kept warm longer. Whereas the smooth, the sun hits and then it just bounces right off. Rough surfaces heat faster because each ray of sunlight or insolation contacts the rough surface more times. So it's bouncing off. All right. Now we come to the fun part. We saw this before in Unit 1, but we saw it in contour lines. Now we're looking at a temperature field map. That's where all these temperatures are coming in. So just like I had to do in the beginning, in the intro, with the contour lines, I had you draw contour intervals. Well, you're going to do intervals here, but they're not contour. They're isotherms. Isotherms are lines that connect equal temperature points. So remember, this isn't connect the dots like what goes like 30, 31, 32, 33. You want to connect all the 30. And sometimes you're going to have to add points or dots to help you out. So the first thing I did, or I want you to do, is draw the 30-degree interval. So I'm going to take a 30 here, a 30 here. Look at this. I'd put a dot between these two, a dot between these two, and a dot between these two. And I'd draw the line something like this. And I'd label it. Label, label, label. Don't forget to label. And then I do it to the 40. So I see my 40s. I put a dot right here, put a dot right here, and there, and then off. Let's see. Yep, 40s. Let's look at 50s. So here's my 50. It's going right here, up, down. I mean, you don't have to be as dramatic as I did right there. Okay, do the next one. 60s, got a loop, 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 up we go and down. 70s, right here, there's just 170, so it makes it nice and easy. And 80s, same with that. This is a big hint. You may see this for your work. All right, so now we're getting into gradient. I know you guys had a lot of issues with gradient before. It's not going away. We're going to see gradient here. You're going to be doing some more gradient. What is gradient? Temperature gradient is the amount of change of in temperature, which is your field value, between 2 points. That's your location. Why do I say this? Well, look at the equations. And temperature gradient, or a gradient right here, is difference in field value over distance and location. Let's look at the temperatures. So I've got 58 and 72. So what I'm going to do is I'm going to subtract them right off the bat. And I get 14 degrees. Now I got to get the location. So I'm going to take a flat edge or something, and I'm going to put it up to A and B, and I'm going to mark it. And then I'm going to take that mark, and I'm going to go down to the scale, or scale it, and I'm going to find that it's about 800 miles. I'm going to put that 800 miles there. See how I put the degree right there? Don't forget your units. Once I put that in, I can calculate it, and it's going to calculate out to 0.0175 degrees per mile. Very important you guys know this gradient stuff. This is step by step. Pause this, look at this, write this down. You need to know how to do this. All right, and last but not least, we're looking at wind chill. This is going to come up in weather outside for you guys, for us, for everybody. Wind chill. What the heck is wind chill? Wind chill is the apparent temperature felt on exposed skin right here due to wind. The degree of the phenomena depends upon air temperature and wind speed. Now, one thing you got to know, this is not an actual temperature. This is a guesstimated temperature, so it's not an actual thing. All right, so this is it for today. Please do the assignment on GoFormative. If you have questions, even if you want to go over the GoFormative with me, hop on Zoom. Email me, class tag me. I do converse through class tag relatively quicker than email. Besides that, I hope you guys have a great day.